Thanks for joining the session. Just a quick intro about myself. I'm from Uber Marketplace. My team built the data platform and the data ecosystem to allow customers to access both the real-time and history data. Today's session is related to serving near real-time features at scale. Scale is a fancy word, and actually that includes two parts. The first one is how easy we can support different customers, how easy we can onboard their requirement onto the data platform. The second part is related to how to tune or optimize a pipeline so the pipeline can produce a huge amount of data. We're going to go through the two parts one by one. Here's the agenda. So for the first part, we would like to allow customers easily onboard the platform. So we need to treat the data as a product. Easy onboarding is the first feature because if that takes too long for the customer to onboard, then we lose the chance to have the real business impact. And also, when customer onboard to the platform, they also want to have the good quality data. The same data can also be shared among many customers. So single data set, but many customers. So we also need to provide a solution for customer to discover the data and reuse the same data rather than rebuilding the same features. For a mature platform, that also need to provide the access control, the ACL, the auditing, and many other features which are not listed here, such as the lineage. For a mature platform, that also need to support all kinds of customers. And how we define the customer profile, we define it by defining the serving contract. When we look at the serving contract, there's multiple features. The first one is data freshness. Second is latency of the access or query. We have other serving contract in terms of data range, the data retention. Here we can see that the four examples. All these four use cases, actually, they use the same data set. But if we look at the serving contract, that's significantly different. So for first customer, they just want to get access the most recent data, say the past 5 minutes, past 30 minutes. They want to get the data back within seconds. If we check the third row, which is another customer, they want to access the same data set, but they would like to access the data trend. To get the data trend, they need to access the data, the daily, weekly, monthly, or even yearly. And they want to get the result back within seconds because they want to see the result on the dashboard. For the last use case, the customer might want to run the ad hoc query through Presto. And they are okay with the latency at minute level. So to provide the support for customer to access the data at scale, we need to support all these kind of customers. And because of the difference of serving contract, we have a huge difference in terms of the data storage and the data solution. And at Uber, we build the solutions to support all these kind of the customers. And also because Uber operates in the transportational domain, so it makes sense for us to access the data as soon as possible. So next, we will focus on the real-time streaming pipelines. Speaking of the streaming processing, so for folks not familiar with streaming processing, here is the key concept of the streaming processing, the window. Why we need to define a window? Because for stream processing, that lead to process unbounded events. The continuous event never ends. It's a huge difference with batch processing. For batch, you process a fixed or bounded input, like the past hour, past day, or past month, but it's fixed. So to support the unbounded events, streaming processing defines the terms of the window. The window answers the question like, what's the data range in terms of aggregation or data computation? And what kind of the aggregation function we would like to apply to the events inside a window? And also the trickle time when the system needs to compute the events inside a window. So that's the key concept of streaming processing. To build the streaming processing pipelines, there are many challenges for engineers. Even there's so many options available, like Amazon Spark, Flink, Kafka streaming. But engineers still need to handle many challenges: how to test, how to deploy, how to keep the promise in terms of SLA. The pipeline also needs to access external servers, need to access the environment, need to access configuration. So how the pipeline can access all this information. Because the pipeline needs to process the message in real-time manner, so it's also important to have the feature to monitor the pipeline, monitor the health of the pipeline, to say, are there any are there any exceptions, are there any hotspots or bottleneck? Last but not least is the backfill. The pipeline will get into trouble from time to time, so that will lead to data loss. And when data loss occurs, so how we can quickly resolve the issue, how we can quickly backfill that. So there's many challenges regarding developing a pipeline. So at Uber, my team actually built two solutions. One is Java-based. The engineer needed to build the Java code. The second solution we call geometric streaming. It's the configuration-based. The customer just need to provide the YAML configuration. Behind the scene, the system will automatically convert that into Flink pipeline. This is the quick comparison in terms of these two solutions and when to use which solution. From the customer perspective, the biggest benefit of geometric streaming is for most of the scenario, the customer can onboard to the system and get the data ready within 1 day. So next, we check the platform we built at Uber, how we support all the scenarios and all the different serving contracts. So the architecture includes 3 major layers, from the injection layer to storage layer and the query layer. It's a super simplified the diagram for the injection layer. So basically, that's define how the stream processing process message, where the data come from. The data could come from the microservice, could come from the upstream pipelines, or from the stream pipeline itself. This data will be published into Kafka, then later on consumed by streaming pipeline. To support this architecture, there's many servers behind the scene, including servers like schema servers, metadata servers, and there are many more. We just call it common servers. Once the streaming pipeline completes the data computation, that will need to save the data somewhere. So that's why the data storage layer comes from. And because we need to support all kinds of the scenarios in terms of the serving contract, so here you can see we have two major categories. The first is real-time data layer, and second is history data layer. Of course, so it's obvious real-time data layer is to support the real-time data access. And depending on the serving contract, we could save data into, say, Elasticsearch or Pinode or other KV store like Cassandra. To allow a customer to access the history data, we have the Spark pipeline to sync the data from the real-time into history data layer. So in this way, we support both the real-time and offline data access. Once the data being put into the data storage, to allow a customer to access the data, we provide the query layer. The query service provides the common function like the rate limiting, the caching, and also the smart routing, because regardless of the serving contract, they talk with the same query layer. And the query layer will route to the appropriate data storage as per the serving contract. And it also does the conversion to convert the incoming request into the corresponding SQL for different storage. So put together, it's quite straightforward from the injection to data storage to query layer. But behind the scene, there's the many servers to support this architecture. We checked the architecture, but that's just one part of the story because we also need to provide the good quality data to maintain a healthy pipeline, to maintain the good data. But what happens if there's some data loss? Our ecosystem provides different solutions. You can see the Lambda, Kappa, and Kappa Plus here. So each one actually deserves its own session to discuss. I just quickly go through the difference. For Lambda architecture, so technically, the engineer need to build two pipelines, one for streaming, another for batch. And so that's a two code base. For Kappa solution, the difference is we replay the message from our data lake into a dedicated Kafka topic. Then we share the same code base among the real-time streaming pipeline and batch pipeline. So in this way, we just need to implement the logic once. But here is the catch. We cannot leave the message inside Kafka forever. We might only save, say, up to 3 or 4 days data in Kafka. So if the customer needs to backfill the data, say, past a week or even past a month, then we need to set up a pipeline to read the message from the data lake and replay into the Kafka topic. And then here comes the question, why not just directly read the message from the data lake? So here comes the Kappa Plus. The Kappa Plus just dynamically replaces the input source, replaces the Kafka input with the Hive input. So in this way, we share the same code base, and we get rid of the pipeline to replace the message into Kafka. This is the simplified the diagram to show the different backfill solutions. We talked about the challenge before, how the engineer when they need to build the pipeline, there's many challenges. So here is the answer from the pipeline, from the platform or from our ecosystem. The ecosystem provides many features. The first one is the dependency injection. We allow the customer to access the dependencies regardless of the environment. It could access the production, access the staging, access from the unit environment, access from the integration test environment. That's the same interface. The second part is the ecosystem provide many common operators, allow customer to compose. The common operators provide common features including the monitoring, the logging, and exception handling. It just makes the engineer's life easier. Same stuff will apply to the sinks. We have common sinks for different data storage. The customer can reuse the same sink among the pipelines. As a platform, we provide some predefined metrics. We monitor the injection rate, we monitor the exception, we monitor the output rate, we monitor the CPU, we monitor the lag. And also, we talked about the backfill solution before. The ecosystem also provides the pipeline management to look after the deployment for engineers. So it should be easy to onboard a new pipeline into staging environment or production environment. Last but not least, the integration test framework. It's super important. Why is it important? Because if you look at the left circle of building a pipeline, the engineer needs to try many stuff, to tune many stuff. So for each round, without the integration test framework, the engineer has to deploy to a staging environment, then check the result. It's quite time-consuming. And with the integration test framework, the engineer can replay the Kafka message and launch the local pipeline and launch the local cluster, which is running on the laptop, so you can get the result immediately. That's the first benefit. And second benefit is this integration test framework allows engineer to build the integration test, which protect the changes and side effects from the pipeline, which gave engineers the confidence to continue tuning the pipeline. So here are some numbers which the pipelines being onboarded to this platform. Now we move to the second part, how we optimize or tune the pipeline to allow that process huge amount of data. So here is one example pipeline that processes 300,000 messages per second. This is not the largest injection rate in terms of, the pipeline. But it has one of the most complicated logic. The reason is, first, there are many windows. Each single message needs to get involved with 63 different windows. The window include from the 1 minute window to 2 minutes window up to 32 minutes window. They are sliding window by 1 minute. And also, at Uber, we map the message to a location system we call H3 or hexagon. And for this particular pipeline, for each message, that's mapped to the home hexagon. But at the same time, the same message needed to broadcast to more than 1,000 different labels. So here you can see huge, the requirement for state management, for the aggregation. Here's some numbers for this pipeline. Here is the logic, the DAG for this pipeline. So thanks for the streaming pipeline and the streaming ecosystem, it's quite easy to build up a pipeline. And most of the time, if you just follow the logic, the diagram, that might work. So in this case, you can see quite clear that receive the message from the two Kafka inputs, then do some keyring smooth, which is a broadcast I talked about before. Then process within different windows from 2 minutes window to 32 minutes window. then eventually you merge that, then publish that. So this pipeline generates 63 features. So the logic is quite clear, but if we put this logic onto production, and that's what we got. We talked about the lag before. If you check the left-hand diagram, you can see the lag just keep going up. And we also talk about this is a real-time pipeline. If the lag above, say, couple minutes, then the data is useless for us. Obviously, that's not good. We need to optimize it. We talked about the integration test before. Here, I just want to say that again. So before tuning the pipeline, should have the integration test there to protect that, just like the unit test. At Uber, we applied a framework in terms of the optimization for the streaming pipeline. At the central point, that's the metrics that collect all the metrics we talked about before that gave us insight in terms of the health of the pipeline, what's the bottleneck of the pipeline. For the inside triangle, that's the three categories, which is not a surprise. That's a CPU, network, and memory. For the offset layer, that's an interesting part. We check them one by one. And each part might have an impact on CPU, network, and memory, or sometimes have an impact on all of the three categories. We check the parallelism first. It just defines how we need to configure how many containers for each individual pipeline. For example, if the input message is 16,000 per second, and if each container can only process, say, 2,000 per second, then you need at least 8 containers. The next is the partition. If we look at the pipeline, we can see there are multiple operators, from the upstream operator to downstream operators. We could pass the message as per the partition. If that's pass the message in the same JVM, that's the most efficient. But if we need to partition with some features like a key by, in that way, which means upstream operator might need to send the message over the network. So that will involve the network and also involve the cost in terms of the encoding and decoding the message. So partition here play a big part in terms of the performance. The next is the garbage collector, how we can reuse the object to avoid the cost of the garbage collector. And for algorithm, obviously, that will impact the CPU, sometimes the memory as well. And the last part is the remote call. Because the pipeline many times need to talk with the external servers. So for some scenario, even the Redis call could be a bottleneck. If the Redis item is too big, or there's some quarter at the Redis site, that might impact the performance of remote call. So when we need to do the optimization for the pipeline, this is the framework we follow. So next, we quickly go through how we actually apply the framework onto this pipeline. We talk about the tunings on network. So here's some practice. For example, for the Kafka message, quite often it has many fields, But if that's not used by your pipeline, then don't pass that. And also, you can consider to encode the message to be a more efficient way rather than use the raw event. And if you can filter the message and do some deduping at the early stage of the pipeline, then this message will not be passed to the downstream operators. So the last one is actually a very effective in terms of the performance tuning that impact on all three categories, from the network to CPU to memory. So if we remember the job deck I shown before, we can see there's a 2-minute window, 4-minute window, and a 32-minute window. So there's lots of the window operation. So which means there's lots of the window state to manage. And also because to have a window, the message needs to be distributed among the network. So that involves huge amount of costs for network, CPU, and memory. So here we replace this window operator with a customer's flap map operator. We totally get rid of the partition in this use case. So that's for the network. And here is for the memory. We can choose use tuple rather than POJO because it's more efficient in terms of the memory. And also, at the early stage, we can consider how to store the message, store the fields or the intermediate result inside the message rather than pass the final result. And the last one is for Flink. We can enable the object reuse, the feature. Basically, when we pass the message from the upstream to the downstream, we want to pass the same message. We don't want to recreate a new message. So that will save the effort for the garbage collect. Here is some tooling for CPU, and we talked about the dedupe before, because we process less message for the later round, so that will save the effort for the aggregation. And we talk about the customer's flat map operator to replace the sliding window. And it also avoids the overhead for window management and also the serialization, deserialization, because this involves a huge amount of cost on the CPU. And another practice is also you need to think about whether you need to avoid the boxing and unboxing, because when that process a huge amount of events, that's really add up. After all the optimizations, you can see that's the job diagram, which much simpler compared to previous one. We get off all the 2-minute window, 4-minute window to 32-minute window, replaced with a normal flat map. So the message from the 1-minute window passed to flat map window is just reuse the same object and passed in the JVM. So that have a huge benefit for optimization. So after all the optimizations, so here is the result. We have a happy ending for this pipeline. So here are the key takeaways. To be scalable, first, we need to build an ecosystem or platform which will allow customer or engineers to quickly onboard and adopt the pipeline or the platform. So they just need to focus on the business logic. The second part is related to individual pipeline, you need to have a framework of performance tuning. And the framework will help you to navigate when you need to go through multiple rounds in terms of the performance tuning. And here's some further readings if you are interested in some technologies I mentioned before, such as U-metric. Because U-metric is a large system, not just include streaming, it also provides the batch as well. Cool. Okay, so thank you for joining the session. So any questions?
Awesome. We have time for maybe 1 or 2 questions.
So you have a data access layer in your diagram. Is that standalone service, or is on the client side that you do the like cache and everything, and the data transformation?
For the data access layer, that includes multiple servers, and each service is a kind of the microservice.
All right, one more thank you for Feng Shu.
Cool, thank you. And